All right, we're almost there. Slowly, students are coming in. Slowly start. So, good afternoon or good evening. Still good afternoon, I believe. And hopefully you have air conditioning. It's not as hot as out there. And okay, fluid mechanics. So I'll start sharing the screen, okay?
Professor?
Yeah.
Just to be clear, are we skipping the hydrodynamic bearing section?
Just a second. I don't hear you very clearly.
Are we skipping the hydrodynamic bearing section that's in the book?
Oh, yeah. The book has more things, and it was never in the, in the curriculum. So I have a remark here in a moment. Actually, okay. If you look at the first slide, I'm saying that we started the chapter with viscous flows, and we're trying to show that there were exact solutions. Those solutions were exact before people started doing the way I do it, which means that, hey, here's the Navier-Stokes equation, we make these assumptions, and this is what ends up. Those models were developed before that. So it is kind of nice that we can group all those models into the same science, or same scientific group. I mentioned that the flow between two parallel plates is a bit a hard sell, because what is infinite? I mean, where you see an infinite. So the application of this thing is really to understand the hydrodynamic bearings, where you have a very tiny film of liquid to reduce the friction between two metal or two solid surfaces. And of course, in everybody's car, we have hydrodynamic bearing. Now, the hydrodynamic bearing is a little bit more complicated, because they actually have a change in the spacing, and therefore there's a change in the pressure. And that is incorporated in the section which is in the book. Again, this is advanced. A direct thing that relates to that is they used to have rotating discs in the computers, and they had the pickup arm. It was actually floating on the disk based on that principle. So that was because that was really more two-dimensional. The hydrodynamic bearing in your car is cylindrical. So we have to do the same thing in cylindrical coordinates. On the other hand, in the book also, there are the two concentric cylinders, which you can look at that as well. So it will give you what kind of torque you need to rotate two cylinders, one inside the other, if you fill it with so much liquid, and that's the spacing and so on. So it has some scientific information about designing bearings. But again, this is just a side remark. I hope I did answer your question. So the simple answer is that, yes, that section is not included. The book is, you're going to find later on that the book has more than what we have. And that's it. So just follow the lecture notes. And I mentioned that we discuss one-dimensional flows, two-dimensional flows. If the flow goes to the same direction, what's the difference? We try to say that if we use one-dimensional velocity, then it really represents the same amount of flow. And in this case, we were able to develop formulation for both the upper plate moving and upper plate is not moving. If the upper plate is not moving, then the flow will move because of the pressure gradient. So that was kind of a start. We introduced the method, and now we're going to apply it to something far more applied, which is the flow in pipes. And this is something which is very important, and we're gonna spend a little time on that one. I started it last time. I'll go over quickly the first portion again, and again, because it's important. All right. So Hagen-Poiseuille flow, 1800, 200 years, almost 200 years, this thing has been around, and I mentioned that Navier-Stokes equation came a little bit later. So he did the formulation, and which is going to be here. Then there was another gentleman that developed some experimental formulation, and we're going to see that things are really working pretty well. Okay, so what's the difference? We're going to do the same thing, but now we're going to use cylindrical coordinate. I described the cylindrical coordinates. It's x direction, radial, and tangential. We assume that the flow to the tangential and radial direction is 0, which is very logical. And therefore, we looked at the equations. Here's the equation. They look really, really scary. But if you look more carefully, so if you look carefully, you cannot be scared, because we said the r is 0, the theta direction is 0. So we end up with actually, and this is also when we end up with dqx dx equals 0. Okay, so if there's no change in the x direction, so the only way that there's going to be a velocity profile if it's going to be versus r. So if there would be a dq dr, dqx dr, that would work, like this one here. Okay, somewhere here. So these two equations also will go away, and here we're going to get a little bit, which I'll describe later on. So once we take all these definitions, here I rewrote the continuity. So that was the continuity, and I just tried to explain that this term, the only one that remains, and therefore a gradient equals 0. These two guys are 0. That's the conclusion. So Qx must be a function of R. And here's a little effort to show what we expect. We already know that the flow between two pipes looks like a parabola. So we expect something very similar. So this is what we sketched out. Again, this would be the radial direction, and this is the x direction. So this would be the velocity profile. We put the coordinate system at the center. Therefore, now we're going to have symmetry up and right, which we did not have in the case of the plates. So this is going to be actually simpler. And then one more time, what I've done here is the equation. I know I'm going to lose it. Here's the pan. So this is the equation again, the Navier-Stokes and cylindrical coordinate. After what I said, we have nothing in the radial and tangential direction. So we assume that the pressure must be constant in this direction, because everything else, there's no velocity in that direction. What's left from that one, that equation here, is only, well, the dqx dx is 0. We already said that before, so nothing happened, nothing from here. Here we can have rho g if you want, but we're going to cancel that as well, because we're going to think that these two represent the same thing. Okay, because this is P is a function of rho g z. Okay, and then dp dx or dz or x, you said x in this case, or okay, let's say it's a rho gx. Therefore, it's going to be rho g. So these two are pretty much the same. And then in this side, actually, from the viscous terms, the first time we're going to have a viscous term, this is all what is left, which is the x direction, second derivative, and then the first derivative. Again, this is a result of the coordinate system. Where did I go? Yeah, okay, this is where we were before. And we claimed that also the pressure now, dp dx is constant, and therefore the pressure must be a function of x. Let me repeat one more time. We're kind of throwing this away. This is a function of x. This is a function of r only. Therefore, the only possibility that this quantity is constant. Therefore, the pressure itself is a function of x, because we can integrate that one here. So these are all kind of speculation. And again, Hague and Poisy 200 years ago did arrive at the same conclusion. They did not do it the same way we do. They say pressure must be constant, and because the pipe is always the same. And anyway, so that's how they ended up. Now, what we ended here is one equation. So this is the same equation, but I kind of rearranged it again. And so eventually we're going to throw this away. Throw this one away. I threw it away later on. Okay, and then what we have here is we have some kind of a versus R term. So we try to take this portion and just simply put it here. So then we can integrate, okay, integrate. So we end up with R dqx with this one, and integral of this one, which is a constant, and R squared half plus 1 constant of integration. Then we again take the R down, so we end up with this. This is just algebra. Same thing here. And then we lost 1 R because we divided by R, and this guy's become divided by R. Another integration, and then we get Q of X, and the 2 comes here, 2 mu, this becomes R squared, another 2. And then A over R is logarithm integral, and then B of constant. So we end up with constant. Then we need to get the boundary conditions to figure out A and B. Again, I recopied that result. And we ended up, this is again high school stuff, just simple integration. Simple integration, we ended up with this. So we need to figure out what is A and what is B, and what are the conditions. We think that at the center of the pipe, there is symmetry. If there is symmetry, then the derivative must be equal to 0. We also know that we require the no-slip boundary condition. So at the wall of the cylinder, or at the contact between the liquid and the pipe, the velocity must be equal to 0. So that's the no-slip boundary condition. So if we want to have this condition, and then we're going to equal capital R. No, we did that one first. Okay, we did this one first. So take the derivative of that equation. So 1 over mu R squared 2 times, and then we plug in here 0. Then A over 0. Okay, logarithm is 1 over R. And it's not good. Doesn't look very good, not convincing. So just a second, where's my pen? Oh, I have the pen, okay. So this will blow up to infinity. So the only way that this can happen is A 0 equals 0. So we got rid of that term. The logarithmic is gone. It's gone. So what we left with is now we left with this equation, okay? And now we substitute this boundary condition that the velocity is 0 at the wall. And instead of little r, we put in capital R. Remember, this is the coordinate R, but it's equal, capital R is the radius of the pipe. Okay, so sometimes students ask me what's the difference between the two. So we substitute that one. And now, simple algebra, we figure out what is B, this thing. So now we actually solve the problem. We have to resubstitute B back here, and then this is the solution. So let's see what happens. Okay, so just a summary of what we did the previous page. We concluded A must be 0, because otherwise we're going to have infinity. And B was this algebraic thing. Substitute This is the final solution. Somebody is making noise. Okay. Now, we're trying to look at this solution. First of all, it's a parabola. So here's the flow which we speculated first. Yeah, indeed, this is the shape. The velocity distribution has a shape of a parabola. Now we proved that, okay? Also, the maximum is reached at the center, which is very logical. Although we assume that there is the shear is, I mean, the derivative is zero, which is the shear is zero, which we assume symmetry. So that's automatically came out. And then the more important part is if you look again at that equation, okay, I just copied it over. So I threw away the rho g term finally. And instead of this, I'm going to use that one. Okay, this one. So this is the equation. And again, at r equals 0, the maximum velocity. So what I'm going to do next, I'm going to say that this term is equal u max, and actually I'm going to change the equation just so it looks good. But actually, it's much better to keep it that way because it has the original variables that we started with. Now, what I was going to say is that we're having velocity. Remember, velocity times the area, okay? Some average velocity times the area is the flow rate. So the most important question people ask about pipe flow is tell me how much pressure drop I need in order to push that much flow in a pipe of diameter so and so. So this is the typical city water problem. And you look at this equation, it has viscosity of the fluid, which fluid you're driving, what is the pipe diameter, how much pressure, and how much is the flow rate. The relation is linear, very much like we had in the flow between two parallel plates. You increase the pressure by 2, the flow rate will increase by the same value, which means the connection or the relation is linear, which is very, very important. It's not easily predictable. All right, let's move on. So we'll do exactly what we did before, is we try to get certain quantities like an average velocity and learn more about the problem. Now, I copied again. This is the same equation I had before. Remember, this is a velocity profile is here. It's a parabola. It is 0 at the wall and maximum in the center, linear pressure. What is the maximum velocity? Well, actually when r is equal to 0 at the center. So very simple. So I just copy this from here and I get the minus sign from here. So clearly this coefficient, if I may call it, is the maximum velocity. Why is the minus sign? Because the pressure gradient must be negative. I mentioned that last time, and therefore that's the maximum velocity. Okay, so what I did here is just to be nice, I derived it again. So if you want to have a maximum, so you have to take the derivative of that equation and make it equal to 0. Make it equal to 0, it's only when r equals 0. So the maximum velocity at r equals 0, which we noticed already without that. So instead of that equation, I can write it down like this. So there's a maximum velocity here, maximum velocity, and then the distribution is depicted by this parabola. That's it, very, very simple. Okay, so we have the equation. I think this is very important. Now, let's move on, plenty of work to do. So now we needed to, remember we did average velocity and things like that before. And so we have the maximum velocity.
Professor, can you go back, please? You said that equation is very important and it's not in the, I can't find it in the book. So I just have to write it down, please.
I think this one is not in the book.
Right. Which one?
This form is not in the book. It's in a different edition.
Right. Okay. But that's the one that you said is very important, right? That equation?
Well, both of them are very important. Both of them very important. And what we're going to see is eventually there's a gentleman by the name of Darcy. I'm not sure if we're going to get there today, but he developed the whole thing experimentally. And it's amazing that how accurately the result will match. Okay, so, but these two equations are the same. This is much easier to remember. And it also explains what is the velocity profile, how it looks like. It's very simple. This will have more details, but would be nice to remember. Okay, so let me go on. And now what we're going to do is get average velocity, get the shear, get the pressure drop thing, all those formulas, okay, which we did for the flow in parallel plates. So how we figure out what is the average velocity? Exactly like we did it the same way. We want to have the same amount of flow. Okay, so we have a pipe, okay, and then there's a velocity profile, and then this is the area going in. So average velocity, like we had before. So remember, Q was the flow rate, which was U average times the area. So here it is, that's what it is. But we have here a velocity profile. So what we need to do is we need to integrate slices by slices and ds. But the ds, remember now, is going to be slices of little bagels, little like that. These are going to be the ds. So, and I'm explaining, here it is, ds is 2 pi r dr. That's what it is. So it's a little bagel. So we just reverse that formula and we say, oh, here's the definition of average velocity is 1 over s and the integral of the flow. Very simple. So let's do that. So we take that formula here and substitute the velocity from the previous page. Remember, that's the maximum velocity here. That's the parabola. This is integral ds. Okay, ds. And here's just algebra. Okay, so we copy everything. These things, multiply everything. We end up with that. Inside the integral, what we have is r squared and this r here, which is the perimeter of that circle. Okay? And so r to the third over r, and r here. This one is this r multiplied by -1. Integrate, that's the result. We're putting 0, so everything is going to be 0 at 0, and we put in a capital R. So we're going to 1/4 minus 1/2, and it's going to be equal and multiplied by 2. That's how we get the 8. dp dx remains, and here we ended up with r squared over mu. So here's the average velocity. Then you look at the maximum velocity is over 4. Oh, here it is. So what we got is the maximum velocity to u average. What is there? Somebody's happy? Somebody's happy. So I'm coming back here. Somebody's fighting. So what I'm saying is the average velocity is 1/2 of the maximum velocity here. Okay. It used to be 2/3 in the case of the flow between parallel plates. Here it's actually 1/2. It's actually more nicer, more elegant. All right, so we said that one. Now, here we can do volumetric flow rate. And this is what I say, this is the importance of that formula. We can claim that the flow rate in the pipe, because at the end of the day, if it's a pipeline, you want to know how much fluid going through. So it's the average velocity times the area. And I just pi r squared, that's the area. We take the average velocity from here. So we end up with this relation. Again, it is linear with the pressure, inversely linear with the viscosity. So I have a fluid, let's say I'm pushing oil of SAE 20, and then I'm pushing SAE 40. The flow rate will drop by 1/2 because the viscosity is increased by 2. the radius of the pipe is to the fourth. So the larger the pipe, more flow can flow in the center. Therefore, it has far more effect on reducing the resistance in the pipe if you increase the diameter. Okay, these are very important conclusions which are completely correct. I will later on clarify that it is all correct for laminar flow what we are doing. Okay, but we'll hopefully maybe today we'll get there, so I can explain it more clearly. Okay, so we just said that here's the volumetric flow, which again I mentioned very important. That's a very important engineering question. And okay, we did that one. So now let's look at the shear. Look at the shear. This is the definition. This is the definition. This is what we have before. Same thing. Same thing. Somebody singing? No. Okay. So minus mu minus u, dq x dr. I just take, that was the formula we used before. Remember? When I try to get equal to 0 and find a maximum. So this is coming from the previous page. So I'm looking at that, and I just put it here. So this one is this, and I put it here. Okay, go through the algebra, r over half. Let me do this. This is the pipe, this is x, and this is r. And velocity profile is parabola, kind of parabola. And now I'm trying to figure out what is the shear. The shear, first of all, it is positive because dp dx negative. So remember, I was kind of hesitant with, or not hesitant, but I wasn't completely happy with the definition of shear in the previous case of parallel plates because there was no symmetry. But here it's completely symmetric, which is how it's supposed to be. And again, we're increasing the radius, and therefore the shear increases. So it's 0 in the center, and it's a linear variation. That's what we ended up. It's a linear term. 0 at the center grows toward the wall. Again, very, very interesting. So here I just said again, 0 at the center, and it's linear. When it's linear, and the maximum at the wall is this. We simply replace this with capital R. That's it. So that would be the maximum shear, which is on the wall. Okay. So we did that. I did A, B, C, D, and this would be number 4. So again, I copied over. This is what we generated last time. So this is just a little anecdote. And then we had the formula for the average velocity. Okay, we have the formula for average velocity. And then I'm solving, excuse me, for dp dx. So this is just turning everything around, rearranging. I get that. Why do I need dp dx? Because here I have dp dx in the formula. So what I'll do is I substitute that one here, and I get an expression like this. Why are we doing it? Because I would like to have something like mu over u. Now, we had the flow between parallel plates. That was the case. And now we have this flow, which looks like that. And I want to compare the shear here and the shear here. Of course, the shear here is a constant. So the maximum shear at the wall, and this was h before. So now I have to take 2r, because that's the spacing. So I have to multiply here. I'm going to have 2 times 2 mu and 2r, which is actually d. I just multiplied everything twice, okay? And nu max. So if I replace that with d, I'll just say diameter, then this becomes 4. So the argument is that if I have the same maximum velocity, okay, same maximum, so here and here, the shear in this case is 4 times larger than in this case. I don't know if you're happy or not, but that's the exercise. Okay, that's the exercise. Now, let's get more serious, because we did answer the question about flow rate versus pressure, but we want to open the discussion for generating our result. What I mean by generating, once my professor, when I was young, which was very many years ago, I don't want to say how, he said that what is engineering? Engineering is that you develop a simple model and then you kind of put some maybe experimental coefficient and expand it to cases which are not exactly the same. Like in the case of fluid, we can go between laminar to turbulent, we can go with friction instead of inviscid and things like that. So these coefficients will allow us to do that. You'll see how today we will get there. So let's go back to the friction coefficient. If you recall, we defined the friction coefficient as the shear divided by, I didn't stop. Divided by the dynamic pressure. So I take, remember before we had 4 mu over r. Oh, and then I took averages of u max, okay? So this is the formula from the previous page. I took it because we needed it in form of velocity. And then just go through square and you end up with this. This is just simple algebra. Again, if we would like to have diameter instead of 2r, we're going to have 16 over Reynolds. And the Reynolds is going to be rho u average in this case, diameter, and viscosity. Okay, and this is a more typical way of defining the Reynolds number in pipe flow. Okay, so don't get confused because of the two. We want to use the diameter. Okay. Now, I mentioned that this is really an amazing result because this compares perfectly with experimental data. Usually up to a Reynolds number of 2000. We'll see the meaning of what I just said in a minute, okay? So, and then I already tried to tell you that it's a foundation for more complex pipe flow shapes and computation. So the final trick, we did that again in the case of the flow between parallel plates, just to see the power, the force balance. So here is a piece of pipe of length L. Okay, and I put everything in a control volume. And the control volume is, of course, stationary. So I'm trying to figure out what are the forces. So I can look at here is the pressure gradient in one side against the other. So delta P times the area, which is pi r squared. How much is delta P? Is dP dx times L. Okay, I just called it delta P, forget about the minus, but it's high to low. So that's the quantity, that's the force which is pushing the flow that direction, okay? Now the flow which is holding the fluid back is the shear, F2. So F2 is the shear on the wall multiplied It's not area. It's S would be the length of the circle. So circle length. Okay, so I should have used maybe small s instead of capital S, because we use capital S for the area. Anyway, so that's the length. How much is the length? 2 pi r. That's the circle. Oh, no, you know what? No, it's fine. Sorry, apologies. This is correct. But then the S is the internal surface of the pipe. Okay, so here the S is slightly different. Okay, so what is the internal surface? It's 2 pi r, the length of this arc, multiplied by L. So that's the internal surface multiplied by the shear, and it comes out dp dx pi rl squared. And of course, it's negative. It's acting to this direction. Exactly the same. So one more time, it proves that the shear must be equal to the pressure. Otherwise, the fluid would accelerate. Okay, I believe that that's it. So that's all the math that we're going to do. Well, we're going to do a little bit more algebra, but that's the math. Okay, so we did that. So let's do a bunch of examples, and then we move on to maybe some other problems. This is not the final form. We are slowly leading into a wider database where we can actually tell the pressure drop in any form or any type of pipe. This is where we're going, because this should be a very important engineering conclusion. So right now, I'm just building up the case. So based on the exact formulation, which we said the laminar flow exact model, here is an example. So we have a circular pipe, okay? And it's 3 meters long, diameter is 1.2 centimeter. And we would like to push 1/2 liter kerosene per minute. So how much is the pressure drop? How much pressure we need? And remember, delta P times the volume is the power. So you can tell right away how much power the pump, what kind of pump you need to buy for this particular project. Okay, so we just look at the viscosity. Density of kerosene is 814, so it's a little bit less than water. Viscosity 1.910 minus 2, so it's not very viscous. Oops, we lost it. Okay, let me get the pen. So viscosity is a little bit here. And okay, so we would like to find out the pressure drop. So we had the formula flow rate versus delta P, which is a linear formula. We just solve for delta P, put it here, and then the rest of the terms are appearing to be here. So this is the equation. Okay, so flow rate, we said we want 1/2 liter, which is 0.510 minus 3 meter cube. But this is per minute, so we have to divide by 60 per second. So it's 1 second. So that's what we have here. Then 8 is 8. It's coming from the integration we had. Mu is 1.910 minus 2. Pi remains pi. R, we said R is 1.2 centimeters. So the radius is 6 millimeters, which is 1,000th of a meter, which is correct, the fourth. Do the algebra, minus 31.2 Newton meters a second. How much is the average velocity? We have, what did he say? Oh, we actually have the flow rate, okay. So we have the flow rate, and then we have the diameter, so very simple. Flow rate, so average velocity, flow rate divided by the area. Here's the area, pi r squared. Flow rate, 0.5, everything is metric, divided by 60 per second. And it's 7 centimeters per second, 7.5 centimeters per second, not very fast. Okay, and then I keep on saying that we trust this to be true for Reynolds 2000. So now let's see if this applies here. So we take the density, we take the average velocity, we take the diameter, divide by the viscosity, and the Reynolds number in this particular pipe flow is 378, which is less than 2000, so definitely the flow is laminar. Definitely what we calculated is going to be the same if we will make some measurements, so it's very accurate. All right, let's do another example. So this is again an example which is based on the fact that you did not have in the book the formula where K is actually the maximum velocity. So then you have to look at that more carefully. But now I already told you that this is the maximum velocity. So here's the problem. That used to be, again, in one of the exams in the past. So we have a pipe flow, diameter is given, and this is the velocity distribution. So we already know the pressure drop and the properties of the fluid, which is actually SAE 30 motor oil. And then we need to calculate the value of K. So if you recall, the original formula had this term, which is the maximum velocity here. So you have to look, at that time, I mean the student in the exam, had to look back to the original formula and say, oh, this is K. And then R square, what is the diameter? What did it say? Okay, here it is. It's 10 centimeter diameter, so 5 centimeter is the radius. Okay, R, 4 times mu, and then we have dpdx is 2,400 Newton meters square, which is Pascal per meter. You do the algebra, you end up with 5. Of units, of course, is going to be meters per second, because this is the maximum velocity. So,
Professor, sorry.
just a second, let me draw it, and then I answer your question. So what we have is, this one is 5. Okay, I'm done. Please ask.
Where is that 2400 coming? Is that coming from the equation for dp or dx, or do you just know
What is
that?
the 2400, 2000? This one, what is that?
Yeah, where is that coming from, that number?
Okay, one more time. So I have a circular pipe, and then it's long. I don't know how long it is, okay? I don't know how long it is. And there's 5, SAE motor oil is flowing inside. What I know is that if I take a slice of 1 meter and I measure P1 here and P12, I will find out that P1 minus P2, which is versus 1 meter, is going to be equal to 2400 Pascal.
Okay, that makes sense. So,
Okay.
but in this problem, it's just given. It's just a given then.
It's given. It's given. So
Okay.
I can formulate the problem that I have a long pipe, and I'm going to apply a pressure which is equivalent to this quantity. Okay. Tell me what is the flow? How much is the flow? Okay. And we also answered that one, but I can pose the problem like that. This would be the engineering question. I want to push this amount of liquid in the pipeline. This is the diameter. This is the properties of the fluid. I have maximum so much pressure available. How much flow can I get? That would be the engineering question. So let's keep on going. Okay. So shear on the wall. Okay. We just take the formula R dpdx. We already calculated. We already know dpdx, which is 24, and then R. We know what the radius is. It's 5 centimeters, so it's 2.5 centimeters divided by 2. It's going to be 60 Newton per meter square. That's the force on the inside of the pipe. What I have done here is actually did it slightly differently with du, dm, dr, and ended up with the same So you take the derivative of the formula, okay, and 10 to the minus 5, and it comes up with the same number, okay, because it's increasing. Okay, so that's just an anecdote. You're supposed to do it that way. This is the formula we developed. It keeps on jumping on me. Okay, we were here. Okay, so one more time. You should recognize that this is the maximum velocity, and then you calculate what's the maximum velocity. It turns out it's going to be 5. What is the shear? You use the regular formula for the shear. And the more important is how much is the friction coefficient. So we go by the original definition in this particular case. Of course, you could do 16 over Reynolds. Okay, but you can do that one here. Oh, here, I do it here actually. CF 16 divided by Reynolds, that's one way of doing it. Or just go by the original definition. So we solved for tau, and then half rho v square, and that number. So it's the same thing, should be the same thing, okay? And then here's just a simple summary. Maximum flow is that one, average velocity is 1/2. We already know that, it's gonna be 2.5 meters per second. And therefore, the flow rate is going to be average velocity times the area. Pi r square, average velocity, pi radius square, and it's going to be 19.6 liters per second. It's pretty fast, okay? And then we solved for what's the Reynolds number, 767, again, much less than 2000. So what we did here is going to be exactly what you're going to find out if you do an experiment, okay? So this is another example, just playing with the same relations. One more, okay, let's do one more. I think I have one more. So just to warm up. Again, these are problems I'm trying to show about the model we just developed. Yeah, it's important, but just to see if it works and how does it work. So we said that this is the velocity profile. Let me just get the prime. We said that before. We developed, that's the formula. Okay, that's the velocity, which is described here. That's the velocity profile. And then we also said that the average velocity is 1/2 of the maximum velocity. Kind of, my line is not exactly. So this is the average velocity. So the question we are posing is at which point, which radius station, the average velocity is the same as the velocity of the distribution is the same. So these arrows are keep on increasing from 0 to maximum velocity. At a certain point, it's going to reach the average velocity level. My drawing, let me redraw it. So here's the pipe. This is maximum velocity. So this is U max. We said 1/2 of it. This is U average. And then we said that this is the coordinate R. And this would be R over R. If we say R over capital R, then this is 1 and this is 0 here. So what is the value of this distance? That's the question. Okay. So what we do is we say, oh, we know, we take that is the formula. We know what's the velocity at that point. It's the average velocity, this. So we substitute it here. It's a known number. We take that one, which is the velocity distribution. And now we have an equations for R, or R over R actually. And you cancel all these things and you end up with 1/2 minus half equal whatever inside here. Very, very simple. You take the -1 to the other side, equal 1/2. So 0.77. So it is going to be somewhere here, 0.7. Okay, so it's not in the middle of that, it's more towards the pipe surface. Okay, this is that one. I think this is the last one. I'm just checking. Okay, that's the last one. Okay, that's the last one, and then we go to more practical issues. Okay, let me just move here something which is in the way. Oh, I'm not supposed to touch them. Here we go. So we have a container. Remember, we did something very similar in the case of the flow between parallel pipes. And this is also the argument of why we lost the gravity term. So we have a large container, and then somewhere here in that area, we're going to have flow, which looks like that. So this is a circular pipe. And we can say that the average velocity, this is the formula we developed, is this, but how much is dpdx? So then we can actually say that the pressure P minus PA is rho G. And in the way we develop things, then this would be X, rho GX. So it's positive. So dP dx is rho G. Okay. So here it is. So what I'm saying is I can take that equation and say average velocity equal, not supposed to do that if I choose a pen. Okay, so one more time. So I convince you that the pressure gradient is dP dx. So now we take rho G is dP dx, and then this term is this one. And the way I did the coordinate system, dP dx is actually, so we lost the minus sign. So what is the average velocity? We just very simply do that. We have the diameter, we have r square, which is 3, so it's 1.5 centimeters square. 8 mu, we know the properties. Here it is, mu is 0.29. And density is, again, it's some sort of oil close to SAE30. And then we just do the algebra and end up with 0.87 meters per second. That's the average velocity. Let's see what is the Reynolds number. Oh. Density, velocity, which we calculated here, diameter, viscosity. Reynolds is 100, definitely laminar flow. Let's look at other quantities. Okay. So how much is the flow rate? But for example, what is the shear? So we use the original formula because we have dP dx. So R half, and of course we're going to put here capital R. Capital R. And we said, yeah, okay, capital R. Oh yeah, no, I did okay. Capital R half. So it's 0.3 divided by 2, okay? And because that's the 3 is the diameter, so I divide by 2. And density, gravity, that's it. That's the formula. How much is the force per 1 meter pipe? How much is the force? Is the area. So the area, the length is 1 meter, which I put here. And then we have the radius, 2 pi r. So that's the inner surface area of a 1 meter long pipe. Okay, that is the shear that we calculated, and that's it. And of course, it must be equal to delta P times the area. Okay, same force. And how much is the flow rate? Average velocity times the area, pi r squared, that's the area. We have the average velocity from here. So we take the average velocity from here. Okay, and then this is the flow rate, so it's 0.6 liters. A liter is 10 minus 3, okay? 10 minus 3 of meter squared. It has 4 minus 4 here, so we move the point, then a similar point to here. Okay, so that is the result. Okay, so that was a very, very simple example, very typical. So, okay, so now let's try to go to things which are far more practical. Any questions up to this point? Anybody? No questions?
You can continue, Professor.
Louder, please.
No questions.
No question. No question. So at this point, we did very similar things, what we did with the flow between parallel pipes. We developed the formulation, we did some examples. These are the typical examples for homework and also for exam. That's it. So now we need to move to more practical aspects and try to generalize what we found here so we can actually apply it to any type of pipe flow. Okay, so let's move on. So it turns out that Mr. Darcy, okay, so I mentioned earlier that the Hagen-Dazs guys are actually studied analytically. They did some measurement, developed formula. Mr. Darcy, though, he was a more practical guy, and he just did experimentally. Now, I'm not showing Darcy's formula yet, but what I'm trying to do is trying to go and eventually get to his formula based on what we did so far. So if you recall, okay, let me just get the plan. If you recall, first of all, that's the definition of the friction coefficient, okay? And we're trying to generate something which is very similar to what we did, but try to get experimental data for the friction. So if we are able to generate experimental data for the friction, then we can answer any question about pipe flow. So that's really the philosophy behind that. Now, the shear. Should I go back? Because we showed that the shear is this term, which is the shear on the wall of the pipe. Remember that? Yeah, anybody?
Yeah, can you go back and show us, please, Professor?
Okay, he's a brave guy. That's wonderful. When I did the shear, I ended up with this formula. This is when I tried to do A, B, C, all the different quantities. Remember that one?
Yes, Professor.
And then I said, I don't like it. I'd rather have it in terms of velocity. So we did that one. But now we're going back to the origin. So we're going to take that formula. Why? Because eventually we would like to have velocity versus pressure. And this one has the pressure on it. Okay. So let me go back to the Darcy story. So I'm trying to show that what we're doing is kind of ends up with Mr. Darcy's formulation. But I'm hiding Darcy's formulation, so you don't know where we're going. So I'm trying to make it mysterious. Okay, so I took tau, which is this one from there. Remember, the friction coefficient was because this is pressure, dynamic pressure. Tau is very much like its force per unit area, so it's very similar to pressure. So that's a non-dimensional number. So you just look around it and then you end up with this same thing. Nothing, we just took the half away and things like that. So now I can look at a pipe of a fixed length. And I can claim that if the length is L, then delta P is simply dP dx times L. So, and I don't have to worry about minus plus. Let's just call it delta P over L, okay? And then, so what I did, I took this quantity and I put it here. So what's left? Left CF times rho U average square, which is this one, divided by the R. Okay, so it's exactly the same thing. All right, so that's it. Now, how about take the rho here, because that's more, we'll see it. Delta P over rho is kind of nicer. That's how Bernoulli had it. And people try to relate to Bernoulli. So why don't we, excuse me, why don't we divide that? So I just manipulate this one. Take delta P and divide it by the rho. And this is what I'm left with. Now, I'm just shooting forward because Darcy did not use CF. He didn't like CF. He came up with something which is 4 times CF. So I just trying to foresee that, and I multiply it by 4. But then I have to derive it. So I put 1, 2 here and another 2 under here. So I put 2 here and 2 here. So I end up with this. 2r eventually is going to be diameter. Okay. All right. So if you buy this, then I can move on. So this was my story. Okay, this is the story. So instead of 4 CF, I'm going to call that F, which is a friction factor. Okay, he called it friction factor. He gave it a different. We called it friction coefficient. He called it friction factor, and the ratio between them is 4. It's exactly 4. That's how it is. L and L remains. Average velocity remains. And he said instead of the 2r, I ended up with a diameter, and he left it with u square and delta P over rho because it looks very similar to Bernoulli. So if our results were CF equals 16 over Reynolds, then his F for laminar flow, so for laminar flow, the friction factor is equal to 64 over Reynolds, and this is exact. This is an exact solution, which also true with experiments. So that's why they call that exact solutions. Okay, so we did that. Now let's go to the final version of Mr. Darcy. So his final version, okay, final version, he did something else. He took that one and divided by G. And the same thing, it's exactly the same thing from here, but I divided, no, he divided by G. This is Darcy's formula. Very important to remember that. Civil engineers, if you ever, any of that is going, any of you are going to do pipe calculation, you're going to use that formula a lot. So one more time, this is a one-dimensional model because he's using average velocity. He forgets about math and all that, velocity distribution. He's just looking at the average velocity. There is another very interesting angle to this formula. Anybody can tell me what are the dimensions here? Anybody? Any A students? Anybody who took the course the 5th time? He must know. 2nd time, anybody taking the course? Any suggestions?
Dimensions for which equation, Professor?
What is this equation?
Dimensions for which equation? The last one right here?
Yeah, this guy. What are the units of this one? The one I circled here. Darcy's formula. This is Darcy's formula.
Would it be newtons per meter squared per second?
I was going to say newtons per meter squared. So, yeah.
This is meters. If you do metric units, it's length. It's length. This is a very, very interesting result. Okay,
okay.
So you're going to appreciate that. Okay. So, and the final version. So I just took, here it is. This is very, very important. That's why people love his formula. So his formula is the same thing we had before, but he added here, and he said that is the loss. He called that the loss, and it's measured in terms of length. I just remind you that the velocity, if you know the average velocity, then that's the flow rate. And if you want to replace that in that formula, U instead of this, then it ends up here. So Darcy did develop Formula 1 and Formula 2, and there is some kind of a loss, which is measured in meters, and either for flow rate or just some average velocity in the pipe. Of course, you can calculate the flow rate if you know the average velocity. What is the significance of that thing? And it's very elegant. Okay, so you're not getting excited. So let me see. So we have a water tunnel in the city, in your neighborhood, and then there is a pipe here, and somehow you open it up and you have a jet. And then delta P is basically rho GH. H. So if there is no friction, then delta P is square of 2GH. Remember that? Yes? That's the free fall.
Yes, Professor.
But because of the friction, you get less. You lose HF. So the losses of friction for the potential velocity or for the potential pressure drop is represented by Darcy's formula. Okay, so it is very, very elegant. And then you use rho and G and the variables for the fluid, the same fluid that is flowing in the pipes. That's why it is so elegant, the formula that Darcy developed. So now we have an approach where we need to solve a whole bunch of problems like that. Very simple formula. Now, please provide me information for that. So F, as we mentioned before, is 64 over Reynolds. But this is only true for laminar flow and for Reynolds less than 2000. What happens in higher Reynolds numbers? So this is what happens. Okay, so I just run forward a little bit. No, not good. Okay, anybody seen that Moody diagram? Anybody? This is a diagram that describes that F for all kind of pipe flows. We'll get to that eventually. But I just want to say that we now developed this equation. And if we figure out F, if we figure out this one for all kind of interesting pipe flows, we can answer the question, how much pressure is required to push so much flow? And how much are the losses? And how can we improve this? So we're going to have a model. And there was a gentleman from NASA, or NACA actually, way back, by the name of Moody, and he developed that particular diagram. We're going to talk about it later on, but I have a few more minutes, so I'll just say something and then next time I repeat it. So before we can continue, this is the time to start explaining what I mean laminar turbulent. So Mr. Osborne Reynolds did a pipe flow experiment. And you're not doing the fluid labs. Actually, recently they dropped that experiment, which I was really upset about. But the experiment is shown schematically. So there's a big water container. There's a little tube. And then you have another tube, the white tube here, that you insert some dye. Here, maybe some red paint. And then initially you have a very straight, nice line in the pipe. But after a while, it becomes turbulent. So what is going on? So here, the flow is laminar and the particles are following exactly straight. There is only one dimensional motion. Later on, the particles get nervous and they start moving left and right. He did many, many experiments, and he found out that if this quantity, which is rho U average, and the diameter of the pipe over the viscosity, if this number is going to be larger than 2000, then you're going to get this. If the flow is less than 2000, you're going to get the laminar case. The range where things are moving from laminar to turbulent is called transition. Okay. Now, the moment you have transition, you naturally start losing more pressure. And here is some, because the molecules are starting to move to the side and then more impingement on the wall. Turns out also the shear is larger. So in general, in turbulent flow, the friction coefficients is significantly larger. And it's true also for external flow, like an airplane. You've heard the story about laminar wing, turbulent wing. If the flow is turbulent, the friction is significantly larger. Here's an explanation, which is, again, I'm just showing it to you so you'll have a clue. We claim that this is the term, the shear term. But in shear, the turbulent flow, there is actually velocity of the transport, of the fluctuation of the velocity back and forth, and to the side as well. And that is some kind of represents the momentum loss due to this side motion as the fluid moves along in the pipe. And that has to be included in the friction. And experimentally, that explains why the friction coefficient, if in this case here versus this case, is significantly larger. I believe that we ended the class. This is a very, very important portion. It is generic, not just the pipe flow, some other things, and I'll repeat it next time. The more important thing today is that we developed the generic equations for the pipe flow. We also showed the Darcy formula, which is an experimental formula. He arrived entirely differently just looking at experiments, and we were able to show that it's exactly the same. Okay, class, thank you very much. Any questions?
Yes, Professor, I have a question.
Yeah.
So I noticed that I'm struggling a little bit with the homework, but I don't know how I'm doing. Like when I submit the homework, how do we know if we're doing well or not?
That's a good question. I'm going to post solutions. I already posted 2 of them. And I think the best way, if you look up the solution and look at yours, I'm not sure how well the grader is checking the homework. And right now, I ask him to split the grade to the grade, how you think the solution is, and also just submission. And I believe I'm going to give more value, more weight for the submission. So based on this discussion with my grader, I think the best for you is to look at the solution that I'm going to post. I think you already turned in 3 homework, right? And
yes.
Today is going to be the 4th.
Today, the 4th one is due, yes.
So probably next week, I wait for a few students, somebody late forgot. So next week, I'm going to post for the other 2 solutions, okay?
Okay, Professor. So basically just look at the solution, make sure that we understand it, but there's more weight on our grade as long as we're submitting what we're doing.
Roughly. I didn't say it very clearly, but you understood it well.
Got it.